Chapter 1.2 is called Powers and Exponents. Here are just a couple of vocabulary words that we will be using when we talk about powers and exponents. A power is a product of repeated factors. And remember that product means the answer to a multiplication problem. So we're going to be doing some multiplying. Base is the factor that is being repeated or multiplied by itself. And the exponent actually means the number of times that base is multiplied by itself. And this is what these vocabulary words would look like. The 3 in this case is what we call the base. It's the factor that's going to be repeated by itself. And the 4 up here is the exponent. It's how many times we're going to multiply 3 by itself. And the whole thing is called the power. And we would say 3 to the 4th power here. And again, we would multiply the base, the 3, by itself 4 times, so it would be 3 times 3 times 3 times 3. Example 1 is called writing expressions as powers, and it says to write each product as a power, and you can see we have 4 times 4 times 4 times 4 times 4. So what we would do here would be to just write the base, which is what factor is being repeated by itself, and that's a 4. And then you can see that we have it 1, 2, 3, 4, 5 times that it's being multiplied by itself. And that's going to be our exponent. So we're going to write that up here, and we would, as a power, we would say that's 4 to the 5th power. Letter B in this example does the same thing. This time it says 12 times 12 times 12. And one quick thing to notice is that in this letter A example, they use the multiplication sign that is the dot. And remember that dot means multiply. In this case, they use the X, which looks more like the multiplication sign that we're used to. But both of those mean multiply. So in this case, again, you've got 12 times 12 times 12. So 12 is your base. It's being multiplied by itself, and it's being multiplied by itself 3 times. So we would call that one 12 to the 3rd power. To the 3rd power, sometimes we also call cubed. So you might hear somebody say 12 cubed in this case. And just since we just talked about this, something to the 3rd power we said is called cubed, like in this example right here. But also remember that if you have an exponent to the 2nd power, we call that squared. So anything to the 2nd power is squared, anything to the 3rd power is cubed. Here are 2 problems to try on your own, and remember that the answers will be on the next screen, but make sure you show any work if you need to. You're just writing the product as a power. You don't have to solve for the value just yet. In example 2, you're going to actually be finding the values of powers. So the first part A, says find the value of each power, and we have 7 to the 2nd power, or remember to the 2nd power we also called squared. So we have 7 squared, and for this one we're going to be doing, that means 7 squared is the same thing as 7 times 7, because we've got 7 being multiplied by itself 2 times, and 7 times 7 equals 49. So the value of 7 squared would be 49. You want to make sure that you're careful. A lot of people make the mistake of accidentally multiplying 7 times 2. So if you accidentally come up with 14, then you probably multiplied your base by the exponent instead of multiplying your base by itself 2 times. In part B, you have 5 to the 3rd power, or remember sometimes we read that as 5 cubed, and that means 5 being multiplied by itself 3 times. So oops, see, I wrote a 3 there. And you don't want to do that. You want to multiply 5 by itself 3 times. And so you have 5 times 5 times 5. And since you can group these, you can think about it as 5 times 5 is 25. And then you can do that times 5. You can do the side math for that. And 25 times 5 is going to give you 125. So 5 to the 3rd power, or 5 cubed, equals 125. Example 3 is called identifying perfect squares, And this might be something that's new to you. So first of all, you need to know what a perfect square is. And it says it's the square of a whole number. That's the definition Big Green gives you. But basically, if you'll think back to what we talked about in some of our earlier slides, remember that anything to the second power is considered squared. And that is because if you think about individual kind of squares there and what the shape of a square is, it would have to have equal amounts on both kind of the up and down and the side to side in order to make it that perfect square. So for instance, this one would have 2 tiles on the side, and this one has 2 tiles across the top, and so 2 to the second power, or 2 squared, would be 4, which is exactly how many tiles you have right in there. So anything squared might change the size of that drawing, but it would give you the same idea. So if you were to bump some of this up here for a second and to do a different size square, you could do 3 tiles across if you wanted to, but then you would have to be able to do the same number of tiles down so that they're equal. Unfortunately, my squares are a little small there because they're squeezed in, but you kind of have this perfect square shape right around the outside there. And so when you have 3 up and 3 across, then you would have 3 squared, and that would be equal to 9. 1, 2, 3, 4, 5, 6, 7, 8, 9 tiles. So that's the general idea, and we're going to get into this next example to look a little bit more at it. When we're trying to determine whether a number is a perfect square, we have to look at the number and we have to ask ourselves, is there any number that could be multiplied by itself, so a power, that could equal this number? So we're looking at 64 right now, and we have to ask ourselves, is there anything that can be multiplied by itself 2 times, so to the second power, that would give us 64? And in this case, 8 times 8 would equal 64, or 8 squared. So we would say that 64 is a perfect square. When we look at letter B, we're trying to figure out if 20 is a perfect square. And in this case, we have to, again, ask ourselves, is there anything that can be multiplied by itself 2 times and get it to equal 20? And in this case, we kind of have to think, well, 4 times 4 equals 16, so that's not going to work. And then 5 times 5 would be the next possibility, and that equals 25, and that's not going to work. And since 20 is right in between those, then that means it is not a perfect square. There is no number, no whole number that could be multiplied by itself 2 times to equal 20. So we say 20 is not a perfect square. For just a little more practice with perfect squares, we're going to take a look at some of the first common ones. And again, remember, anything can be a perfect square if you can multiply your base here by itself 2 times, so the exponent 2. If you can do that, then that value would be a perfect square. So 1 to the second power, or 1 squared, is the same thing as 1 times 1, and that's equal to just 1. And then 2 to the second power, right here, is the same thing as 2 times 2, and that's equal to 4. And you can keep going right on down the line. 3 times 3 is 9, 4 times 4 is 16, 5 times 5 is 25, 6 times 6 is 36, 7 times 7 is 49, 8 times 8 is 64, 9 times 9 is 81, and then you get 10 times 10, which is 100. And again, you can actually keep going on and on and on, and any number times itself, or to the second power, would still be considered a perfect square. But this is a list of the first 10 perfect squares that you might come across. And just to do one extra example to make sure we're getting the hang of these perfect squares, we're going to check out this question, is 50 a perfect square? So again, we're going to come back to this list that we just made of the first 10, and we're just going to get to know these a little bit. So we're looking for 50, and we can kind of look down our list here, and we can see that 7 times 7 is equal to 49, and 8 times 8 is equal to 64, and since that puts 50 right in between those two, when you're thinking about it, it means it's not a perfect square because it's not either one of those, so nothing times itself would equal 50. So then we would say, no, 50 is not a perfect square. Here are a few more on your own problems to try out, and remember to use side math, especially when you're finding the value of the power. I know a lot of us say we're good at doing some of the math in our head, but some of those numbers will get big pretty quickly, so don't be afraid to show your work and make sure that you're doing it correctly each time. Here are all those answers to those on your own problems that you just tried.